Recording now. So yeah, we're very happy to have Jacinta Holloway-Brown from the University of Adelaide this afternoon in the Statistics Across Campuses seminar. And Jacinta is a lecturer in the School of Maths, and her research expertise focuses on hybrid approaches of machine learning and Bayesian inference and spatial statistics to model biodiversity and environmental change. So Jacinta, the floor is yours.
Hey, thank you. Can I just check again that you can still hear me? I'm sure you can, but just in case. Great, thank you. Okay, thank you very much for having me. So I'll be speaking today about our method, which is a hybrid of machine learning, spatial statistics, and Bayesian framework. It's called Stochastic Spatial Random Forest for detecting remotely sensed forest change despite missing data. And it's joint work with distinguished Professor Kerry Mengerson and Dr. Kate Helmstead at Queensland University of Technology, which is where I was before I took up this position at University of Adelaide. So the motivation for this work has actually been a long time coming. So I've been working with the United Nations in various different capacities since 2015. And they have these Sustainable Development Goals, which are goals that the UN and World Bank would like all countries to reach by 2030. So as you can see on the slide, these are some very big ticket items that they're aiming towards. So for example, no poverty, zero hunger, climate action, very big and topical goals. But within these, there are some sub-indicators and things that we can monitor and measure to see how we're tracking towards making progress on these things. So the SDG, the Sustainable Development Goal that my work is related to, is number 15, Life on Land. And looking at forest monitoring in particular, so Sustainable Development Goal 15 is all about protecting, restoring and promoting sustainable use of our terrestrial ecosystems. And so that means things like sustainably managing our forests, halting and hopefully reversing land degradation and biodiversity loss. So there are some challenges to large-scale environmental monitoring. One of them is imperfect or non-existent data. So we might have disparate and incomplete data. We don't have enough. The data that we have might be poor quality, it's in the wrong places, or it's at different spatial and temporal scales. So we have maybe the information that we need, but we can't see it all at the right place at the right time all at once. It might be limited, or we have no available funding to collect any more data, or in fact, any data in some cases. And sometimes critical regions that we really need to monitor for these environmental goals, they're just too remote or too difficult to physically access. So using satellite images is a really wonderful opportunity to get around some of these problems and achieve our environmental monitoring. Satellite images are available for free globally, which makes them a really useful and open access data source. We're able to find insights over large, remote and restricted geographical areas. So those places that we can't physically get to boots on the ground, we can still get a picture of what's going on. And as the sensors become more advanced, we have data at higher resolutions and even more frequently. So the problem that we have though, with these free satellite images, which we have a really long time series of data from these satellites, we have data going all the way back to the 70s and 80s at very different resolution to what we have today, but it's still available. Now, what you can see in the visualization here is a NASA cloud product, and this product shows the average cloud cover, in this case, across each month over a number of years. And so where you can see white, that is cloud cover, and where there is blue, that's where the satellite's able to get an image of the Earth, what's underneath the clouds. And so the problem is that, so a study of 12 years of satellite images has shown that at any time on average, 2/3 of the world is covered by cloud. So we can't see what's happening underneath. And what that gives us is these huge black holes in the satellite images where we can't see what's going on. So it's a really promising data source, but it suffers from missing data very regularly. And this is just a still of what it might look like. And this is the average cloud cover for a 1 week period back in 2020. So you can see that For a lot of that week, a lot of the Earth was obscured by cloud. Okay. And so we need ways to fill in this missing data, right? So the remote sensing approach to filling in what's missing is called compositing. And so basically how this works, I'll use a really simple example. So let's say that we have an image. This is of an area in June in Queensland. And so we have a picture of the area from May 2011 and one from January in 2008, right? And so we can see in this bottom section of the image that actually quite a bit of change has happened on the ground, because the spectral signature, the amount of greenness that we can see, is quite different between these points in time. And we would expect that because they're temporally quite far apart. But the compositing approach in filling in the missing data, say that bottom section was covered by cloud, what we would do to fill that in under this approach is we would set it all to NA, and then we would take the observed values of the same pixels, so matching them up by their lat and long, and we would paste that into the 2011 image, and then we would treat this whole image as if it was taken in May 2011. And so there are clearly issues with that approach because, as we can see, because we know what the ground cover looks like in this example, they're actually very different. And so there are some quality issues with making these assumptions that we can treat the pixels as being taken at the same point in time. But sometimes that's all you can do because we don't have another source of data available. So there are a few things I wanted to talk about in terms of using the images, because there are a few ways around the problem with the missing data. So the way that I've gone about it is looking at statistical ways to fill these gaps. There are these images called radar images, which don't suffer from the cloud cover problem because basically how they work is the satellite shoots a beam of light through the cloud and then measures how quickly it bounces back. And based on those measurements, it tells us something about what is on the ground underneath. So it's really good for things like biomass, identifying where buildings are, things that are taking up more. It's sort of like a 3D measurement. But the problem with these images are that they're black and white and they can be really noisy because they're measurements taken through the cloud. So there's issues with water vapor and other things that create feedback and noise. And because we're wanting to monitor forest cover, which is something that is a lot more straightforward to see in an optical image, that's what I'm focusing on in this project. The other question I sometimes have is, why don't you just wait until there is a clear image? So don't worry about filling what's missing and just wait until you can see it again. The problem with this watching and waiting to see approach is that in tropical regions, which are usually where the forest monitoring is really important. So for example, in the Philippines, where there is a lot of deforestation, and that's done for really good reasons, such as farming and being able to feed families and earn a living, but there are also really serious concerns with landslides. And so when you have these changing landscapes and you have cloud cover that's persistent a lot of the time, we can't really afford to wait until we have a clear image, because that might be, weeks or months apart. So in terms of a statistical approach to filling the gaps in the images, there are traditional geostatistical methods called kriging methods. And these are sort of the popular statistical methods for doing image interpolation, so filling these gaps. And these methods predict the values of the unobserved data points by considering the known values of observations in the neighbourhoods around it. These methods are they're useful and they're effective, but they have some computational scale and assumption limitations specific to satellite images, so they're not really suited to that problem. And so we've developed an alternative decision tree approach that is fast and accurate for images, and it's also very scalable, which is very important for this application. So there's sometimes confusion about why we even need methods for filling the clouds, right? Because if you go to Google Earth Engine or Google Earth, then you can see exactly what's going on, and you might have the impression that it's easy just to look online and you can get a complete image for anywhere in the world. The free images that you can get at the moment anyway are raw and unprocessed, whereas satellite image products are already processed and they don't have any missing data. Because someone has already done that job. However, there are some assumptions behind these products. So the gaps could be filled using one past observation. They might be the average of many past observations over months or a year. They're definitely really useful. And if you can get access to a product that covers the feature that you want to monitor, so maybe that's water quality, maybe that's forest cover. If you can find a product that exists, that has been pre-processed and it's for the area and the time period that you are interested in, then that's great. Unfortunately, it just is rare that it will be provided for the particular problem area and time frame that you're interested in. So I just wanted to clarify the difference between the images and the products. So to summarize some of this background, detecting landscape change is hard because it's difficult to collect data in the field at the required spatial and temporal scales. Satellite images are a free data source, but parts of them are persistently missing due to clouds. And we can fill in the gaps based on the past images, but the past is often not an accurate predictor of sudden changes. So if we're looking for things like forest clearing, then looking at the past is not going to accurately inform what we're looking at now. So what do we do? Right. So this recent paper, as I said, joint work with Dr. Kate Helmstead and distinguished Professor Kerry Mengerson. It's called Interpolating Missing Land Cover Data Using Stochastic Spatial Random Forests for Improved Change Detection. So this is our new statistical method for filling these gaps in images. It's fast, it's scalable to millions and billions of observations, and it quantifies uncertainty, which is a really additional benefit that a lot of current methods don't have, particularly in machine learning. You'll sort of get a classification and that's really the end of the story. When I say that it's fast too, I think it takes probably 3 minutes to do a few million observations and get a probability of forest cover for those. So it's very quick and you can run it on a normal laptop. So our method in 3 steps. So we've taken an effective decision tree method for satellite image analysis. So that's random forest. We've added some spatial information. So that's a spatial random forest that underpins part of this method, and then laid in a stochastic framework. So combine all of these things and you can enjoy accurate predictions with quantified uncertainty on top. And that's the stochastic spatial random forest. So how the method works overall, so it uses a weighted combination of past observed data and current model predictions to detect forest clearing events more accurately than the current remote sensing method. So that was compositing that I spoke about. So I think there's still definitely a place for that sort of approach because it enables you to look at the most recent observations of an area. And we know that, all models are wrong, but some are useful. So it's sort of combining the strengths of learning from the past, looking at a model of the current state of things and then putting these things together. So predictions of the current missing observations in our images are based on the spatial relationship between these points and the observed sections of the current image. And the method also learns from the past and includes all of that information together to produce a probability of each type of land cover. Right. So why decision tree methods? Why not a neural network or something like that? Decision tree methods are really popular and accurate for classifying features in satellite images. They're flexible, they're fast and non-parametric, and they're easily scalable to big data problems. They're also a bit more explainable than other machine learning approaches. Some examples of their uses include identifying land cover, specifically mapping forest cover globally. There's the Hansen et al. Map that you might have seen. That's global forest cover. And then also for identifying land use classes such as agriculture, built-up areas and water. So using decision tree methods for satellite image analysis is well established as an accurate thing to do in the literature. Right, so simple decision trees, you probably would have seen these before. So the idea is that based on these simple individual decision rules, which on their own would not be particularly accurate, by combining many of these trees, you can get more accurate predictions. So if we have a simple decision tree T, it will classify an observation X based on the sum of a few things. So we have our gamma J, which is a fixed value. So for example, here, this value of band 4, which in satellite images, you have multiple bands that measure color and other things. So you might have your red, green, blue, infrared and near infrared, and interpreting these bands tells us different things about the land cover we can observe. So anyway, the gamma J is this value here, the 1572 of band 4. I is an indicator function that will be 1 if the condition of this rule is true and 0 if it's false. And then Rj are values of the different variables that we have. So for example, if we have an observation X, a pixel, then the decision tree will consider it first in relation to this decision rule. Is the value of band 4 for this pixel less than this number? If it is, then the indicator function is equal to 1, it's true, and then it gets classified as being bare soil. If this rule is false for that observation X, then the method moves on to the next decision rule and considers it in relation to that, and so on until all of the observations have been considered and into these final destination nodes, so classified as being either bare soil, cotton, shrub, or pasture. And so a random forest then is an ensemble of these many simple little decision trees, and it draws a bootstrap sample, so it can reconsider the same observations more than once if they're randomly selected. And so that gets away from some of the issues with trees, which is overfitting. And it fits the data by randomly selecting from the set of variables that you have. To assign an observation to a class, the random forest takes the average response or the majority vote of these many decision trees. So how this works in terms of, because it's a supervised machine learning method, so you will do a training and testing phase. And so in our context, we train the model on the observed pixels that we have in the current image. And then we use that to make predictions about the missing pixels that are underneath the clouds. So the training process basically involves taking a full data set of all your observations. And then you can take a random sample of the data, splitting that into a training set where you have the class labels. So the model is able to see what each pixel is classified as. So in that previous example, whether it's, shrub or cotton or soil, for example. And then also the testing set where we don't have the class labels. The model is then fit to the training set where it knows what the answers are. So it learns from that training set, and then you use it to make predictions of the testing set. And you can then use that model on other additional samples as well that it hasn't seen before. Okay, so I'll speak a little bit about the spatial random forest component. So that is the model that we fit at the present image. And then that is combined with data from the past to make the predictions and the probabilities. So this is a paper that we published about spatial random forests, and that's joint work with the same collaborators, but also Dr. Michael Schmidt, who's at the German Space Agency. Okay, so with satellite images, clouds, and missing data, this is a photo just taken out of the window of a plane, but it shows the idea quite well, I think. So we can identify land cover in satellite images based on the colours that you can see and the near infrared values in the images, so the spectral bands that I've spoken about. But where there are cloud shadows, say for example, this bottom right-hand corner of the image, the spectral bands are not measured. So we just don't have information about what we can see there. And this missing data problem occurs for all of the spectral satellites, so Landsat 7 and 8, and even for the newer satellites such as Sentinel-2 and Landsat 9. But the good news is that even when the spectral data are missing due to the clouds, we still have the latitude and longitude of every single pixel. So even if they're coming up as blank, we don't have a measurement, we still know where they are. So what we do then is we fit the decision tree methods to a training sample of these observed ones. So for example, at the edges of this cloud. And then that allows us to get actually quite accurate predictions of the missing pixels. Because looking at what's around it is really actually very informative for what's missing in the middle. Oops. Okay, so why do we include the spatial information? Well, because of the first law of geography that tells us that things that are close to each other are more likely to be similar than distant things. So in this photograph, for example, we have forest in this clump in the middle, and we have some agricultural land at the border and some cleared land in the top left. Now, standard models that don't factor in the spatial information would treat all of these pixels as independent. But spatial autocorrelation and just visually looking at the image tells us that this is not the case. So actually there's a lot that can be gained by including spatial information into our model. So to summarize the spatial random forest, it outperformed another decision tree method that we considered, which is called gradient boosted machine, and also a traditional Kriging approach that was inverse distance weighted interpolation. And so that was for multiple scenarios. That was for different structures of missingness due to different cloud cover types. We found in our case study that like obviously we knew the true values of the missing pixels because it was a simulated case study. So we simulated our own clouds. But for real missing data, we have uncertainty. And so that was a really important piece for future work, because in a real scenario, when the data are truly missing, making a prediction is one thing, but we know that there is high uncertainty. And when we're trying to monitor important things like land clearing, issues with deforestation, we really need to know how certain or not we are based on the model. And also when cloud cover is high and there isn't enough visible image to train on, then we need to use a different method. So we've extended that method. The first case study was just doing a binary question. So was it grassland or forest? But we extended the spatial random forest method to multiple land cover classes in South America. And it does work for multiple classes with some limitations. So when we have large amounts of missing data and many imbalanced classes, then we need something stronger than just the model because it does have its limits. Right. And so that brings me to the next step, which was the stochastic spatial random forest. Because we know in some cases when we have high cloud cover and when we have many classes that are imbalanced, we can't rely only on the model to tell us accurately what's happening in the images. But likewise, when we have clearing events, other things that are happening suddenly in the landscape, it's not accurate to use only past information. So in this approach, we're combining both of these things to fill in the clouds. It quantifies uncertainty of our forest cover estimates, which, as I said, is really important. And using a weighted combination of the past observed data and the current model predictions enables us to detect forest clearing events more accurately than the compositing remote sensing method. Our method can be used for any image in any region, as long as we have some training data, either from the past or currently. And we can use it to prioritize field data collection by highlighting areas of uncertainty. So in the paper, we looked at a case study in Queensland in an area called Injune. So this region is home to 260 native Australian species. So it's actually really important for biodiversity. And we also had some prior knowledge of this area because my collaborator on the first paper, Michael Schmidt, had actually been to the area in person. So we did this study during COVID lockdown in 2020, and a lot of the work was done. So unfortunately, we weren't able to get there in person, but that's yet another case for using satellite images, because there will be all kinds of reasons that you can't go with boots on the ground to look at an area. So on the right here is just an example of one of the images that we had for the Injune site. And that was from one of the free satellites. So I'll talk about the cloud simulation. So to test the accuracy of our method, we need to know what the real answers are so that we can tell how close or far our method came to the truth. So we did 2 lots of simulation. We simulated different types of clearing. So we considered 3 different scenarios. The first was with no clearing events, so just natural fluctuation, whatever happened with the land cover over time between the images we were considering. The second was clear felling, which is where the trees are cut down and the surrounding area is burned. So there's no sort of surviving vegetation for that type of clearing. And then we also considered clear felling, tree thinning. So that's where only the trees and larger shrubs are removed. And that's often done in agricultural scenarios to try to divert the energy into other plants in the area. So in addition to that, we simulated our own clouds independently of the image data. But what we did is we used, as you can see across these images, we used the same cloud pattern so that it was a fair comparison of how well the method did at detecting the clearing events and the natural fluctuation rather than examining different amounts of cloud. And that was partly because we've examined that in previous studies. So to simulate the clouds, we use a distance grid and apply a multivariate normal distribution that is spatially autocorrelated with covariance that declines with distance. And that's just how we made the cloud patterns. In these images, you can see the legend for the different types of land cover, but the one really that you would notice the difference is in the soil class, which is brown. So in the first image, which we didn't make any changes to the land cover besides the cloud simulation, there are just some little natural pockets of soil. In the clear felling, it's very clear to see the fenced off and burned area that's been simulated. And there's also an increase here from the original scenario with the simulated tree thinning. So all you really need to know is that we simulated different clearing events and we simulated our clouds so that we could compare how the model performed in different situations. This is the workflow for the model. So how it works is we have our image, which has simulated missing data, and then we have another prior image from a previous date that has been completely observed. Based on these images, we calculate a greenness measurement. So that's normalized difference vegetation index. It's a measure of how green or not the vegetation in the images is. And based on some thresholds that were provided specific for Australian vegetation by remote sensing scientists who know a lot more about these things than me, I followed their threshold rules to create some class variables, which were in the slide that you just saw. From here, we create training data sets. So these are samples of the observed images at the edges of the clouds to train the model. We fit the spatial random forest that I spoke about to the first image where we have missing data. That's where we want to fill in the missing sections. And from the random forest, you can get probabilities of each land cover class. And then we also take the prior data. So for each pixel that we're trying to fill in the clouds, we have 2 bits of information besides the lat and long. We know what it looked like in the last observed image, and we know what the model thinks it looks like now. And we take those 2 things and we put them together to make a combined conditional probability distribution for each land cover class for each pixel. And so what that gives us in the end is 2 things. So it gives us a probability of the land cover for each of the classes. So actually it's more than 2 things, but a probability, and then it also gives us a prediction because we classify each pixel in the end as belonging to the class that has the highest probability based on the analysis that we've done, combining the past and the modeled estimates. So our method constructs a beta distribution. So with a beta, we're considering 2 options. So for each class, the model considers, is this pixel, does it belong to this class or not? So it's a binary yes or no scenario, but that's for each of the classes. And so using the probabilities from the random forest and some variance that we derive from the image, we calculate our parameters alpha and beta. And so what that gives us then is a posterior probability of each pixel belonging to a class at time t. So in our image where we have the missing section, based on what we know about it from the last image, so t-1, right? And so then we get our posterior mean based on our alphas and betas that we have derived based on our probabilities from the random forest and our variance. And so we interpolate our missing values in our image at t by assuming it will be equivalent to our posterior mean value. So just our value for t given what we know at t-1. Oops. All right, so in terms of results, where there was natural fluctuations, so no clearing had occurred, there wasn't any sudden change, past land cover was actually quite a good representation of the future in this scenario. So in the plot on the left, the existing method is the compositing approach in green, and ours stochastic spatial random forest is in orange. And so we can see that actually our method had either similar or a little bit worse accuracy than looking at the past using compositing. And so that is something to keep in mind in the natural fluctuation scenario. However, when significant change occurred due to our clearing scenarios, our method was actually a lot more accurate than compositing. And this is somewhat expected because the past is not a good representation of what's happening in the future in these scenarios, because there has been a sudden change in the landscape where trees have been removed. So we can see with the clear felling, the more dramatic clearing scenario, our method was significantly more accurate, as you can see from the figure. So compositing is in green again, right down the bottom. And our method is a lot more accurate in orange up near the top. For tree thinning, the difference was less pronounced, but it was still very noticeable. Yeah, so really what this tells us is that if you have a scenario where there's natural fluctuation and no changes occurring, you're not worse off from using our method, particularly because we have the ability to quantify the uncertainty about our estimates. But importantly, when a significant change has occurred, our method is much more accurate than only looking at information from the past. And importantly, we can use our method anywhere that we have images, and it's able to quantify that uncertainty. So this is an example of how you can display the results. So our model produces probabilities of each land cover class, as well as the final classification into a category such as, forest, grassland, dense forest, etc. And we can use the results that we get to produce maps of predictions, highlighting areas of high and low certainty. So for example, here in the right panel, so these are the same random sample of pixels. So the reason the whole plot isn't full and there are white sections is they're not the predictions for the whole area, they're a random sample. So we can see in this right panel, looking at the probability that each pixel belongs to the pasture class, there are areas where it's a very high probability, so close to 1. So we're quite certain about that classification based on the model. And then we can also see, for example, through the center of this right panel, that there's a very low chance of some of these observations belonging to the pasture class. So that is quite clear. In this example, in the left panel, through the center here, there is, based on the color scale, the probability of these pixels belonging to the forest class is somewhere in the middle. It's around 0.5. And so we're not too certain about that. And so depending on your appetite for risk, what the scenario is, if you make a decision based on modeled results without verifying in the field what's happening, if the consequences of that are high, then you might have less appetite for risk and you might want to prioritize collecting some field data for the areas where the model is uncertain. Which brings me to some future direction for this work. So looking at land cover probabilities and mapping uncertainty. So our results are produced at a pixel level, which in some satellites is a 30 by 30 meter area. In some of them with higher resolution, it's 10 by 10 meters. And they're also georeferenced. So it's possible to plot our probabilities of land cover in various ways. And so what I'm looking to do next is to do a case study example where we're able to layer a map of ground truth samples and corresponding satellite images to highlight the areas of uncertainty. And also to identify areas where the ground truth, so data that's been collected in the field, and the model agree and disagree. And the idea is that this information can then inform adaptive ground truth sampling designs. Adaptive sampling designs are commonly known for its use in medical trials, and it involves changing experimental designs in response to collected data and outcomes to reduce costs and improve overall efficiency while maintaining the validity of an overall study. And so why this is important in the Sustainable Development Goal context is that we really need to quite ruthlessly and efficiently prioritise ground truth collection over large areas over time, because a lot of the countries where the monitoring is really needed and the people are focusing on using free data that comes from satellite images, there is such limited or no funding available to collect data in the field. So any way that we can find, efficient and free ways to plan more effective ground truth data collection is really valuable. So this is from a discussion paper I presented to a UN expert group meeting last month. And so we're talking about adapting the Earth observation analysis pipeline by using this method, the stochastic spatial random forest. So how it works usually is that you have a ground truth sampling plan. So you would, plot out your transects or whatever the approach that you're using is. I'm not an expert at any of these things. I would be working with people who are. And then you look for either a pre-processed satellite image product. So that's what I was talking about earlier, where someone has already filled in the clouds and they've made a map of your area. So if that's available, then you go on ahead and do your image analysis. If it's not available, you can use a method like ours to do the pre-processing. So to fill in the cloud gaps, get your land cover estimates. And then from here, people fit a machine learning method quite often, and that's because they're not just because they're popular, but because they're scalable to satellite images. They can work really quickly and well for millions and billions of observations. And then people get their modeled results, and then they validate those results based on the ground truth data that they have from the field, if it's available. And usually the pipeline ends there. But what I'm proposing is that what we could do to try to help improve efforts towards monitoring the SDGs using the satellite images is to adapt the sampling plan based on the validated model results that we get from our method or any other appropriate method. And so then that would feed back into the pipeline again. And so then what that might look like is if you already have, say, a standard sampling plan that you use, and we then run the model for the same area, if those things agree, so the model is correctly picking up what has been identified in the ground truthing, then perhaps for a period of time, which I don't know how long that should be, that would be, to be worked out with experts, but maybe the resources for doing those ground truth sampling could be redeployed to other areas that the model has identified that's more uncertain, or even for areas that are easier to physically get to, it could be directed there. Maybe the model results could be used for the sections that are too difficult to access by people. So it's sort of this idea of combining all the different tools that we have at our disposal to try to get a better outcome for monitoring these really important goals. Oops. In other future work, so I'm considering how these statistically rigorous techniques to fill missing data and quantify uncertainty might translate to satellite images of other environments. So maybe in Antarctica, at University of Adelaide and at QUT, where I was until recently, we have the Securing Antarctica's Environmental Future Research Centre. And so they're interested to know where these methods and images can help, and where do we need to adapt our approach? Because actually cloud cover is a really persistent problem in Antarctica as well. And there's also interest to know whether we can use satellite images and these types of methods to identify penguin colonies. Right. So to summarize, filling missing data in satellite images is a really challenging problem. It's necessary for us to solve it because frequent large-scale ground truth collection is impractical and sometimes impossible for various reasons, including the cost and lack of physical access to regions of interest. And the past is the best predictor of the future, except for when it isn't, and we've had significant change in the landscape. Providing uncertainty measurements is useful for interpreting results and creating adaptive sampling plans that are responsive to changes over time. To summarize the method, our method is based on model results of our current missing data and prior observations of the same pixels. It provides more accurate and robust performance than compositing for substantially changing landscapes. Our method can be used for any image in any region, provided that we have some training data, either currently or from the past. And our method can be used to prioritize field data collection by highlighting areas of uncertainty, and it accurately identifies forest cover change over time. In the case studies that I've done today, we have been using simulated clouds, but there's a lot more that we can do beyond this. And we can explore our method in environments beyond forests, anywhere that we have available satellite images. And so I think there's a lot of opportunity to explore this further and see what else we can do and test the limits of the methods and to hopefully get a better outcome for everyone trying to monitor these environmental things that we care about. And these are some papers that are relevant to my talk. Thank you very much for having me.
Thanks very much, Jacinta. It was a really interesting talk. Are there any questions from the audience?
Yeah, can I ask a question?
Sure, go ahead, Robert.
Thank you. So this is a great talk. So to do something, to actually attack something something more easy, you can apply your methods to, say, time series models, right, where there's missing observations.
Mm-hmm.
And I wonder how, because even there, things can get, if you've got lots of data, they can get quite slow. I wonder how they'd perform on something as easy, in quotes, as that.
I do too. That is actually a good idea. Thanks. Yeah, it's something I'd have to look at for sure. So I think I've seen you speak at an ASIMS event.
Could be, but yeah. But anyway, really nice talk.
Thank you.
Are there any other questions?
So yeah, well, I won't ask unless nobody else is asking something.
Sure.
Well, I've got one just before Rob goes in again. Yeah, thanks. That was a really interesting talk. It was just a question about the whole cloud and cloud shadow thing. So they would each be a problem, would they? So, like, if the image isn't coming from the direction of the sun, then some bits have cloud and some bits have cloud shadow, and so you've got to take account of both of those, and you treated both as missing values. Is that what happened?
Yes, yeah, correct. Yeah, so they're both a problem. Not always at the same time, but yeah, they're both. So there are some methods that are like a step before ours, and they'll differentiate between cloud versus cloud shadow. But I've found in practice, and from speaking to my, well, he was a supervisor on my PhD, actually, Michael Schmidt, in practice, it all needs to be filled in. So we've just treated it as the same, but yeah.
Are you able to reliably recognize cloud shadow? Because I guess you've got to automate that process, do you? Like the recognition of where a shadow is rather than just something that's darker.
Yeah. So you could do it with this method. I haven't actually tried it, but you could do it because you can train it to identify whatever you're looking for, basically, provided that you can give it a decent amount of examples of what it looks like. And so that might be, I mean, I don't have a prescriptive number, but I just mean, like, I don't know, even 50 would probably help. Like, it couldn't just be 1 or 2. You'd need to have enough examples, but there are different oversampling techniques that you can do to give the models a better chance of identifying the minority things you're trying to find. But unfortunately, a lot of the time, finding cloud shadow or actual cloud is not in the minority. So it would be quite an easy training task, I think.
Yeah, cool. Thanks.
Thanks.
Robert, did you want to jump in with your question?
Sure. So suppose that you've got spatial data, but suppose you've got spatial temporal data, which you probably have, and things are changing. So you're at a certain time point with your spatial data, and then you're getting more data. One interesting question would be, what's the minimal amount of extra data that you need to get to be able to have some certainty about what's happening? I mean, this applies to all time series situations, so it applies to spatial temporal, that when something happens, you often don't know for sure if it's, but then you go on a few paces, and you don't want to wait till the end of the period like the patient has died or something. You want to catch it, not exactly when the stroke or whatever happens, but as soon as you can. So the question is to give people guidelines, or to give yourself guidelines on how much you need before you're fairly confident.
Sure. So, I mean, there's a few ways to think about it. So it depends. It can be how much more ground truth data do you need, so the things you can collect in the field, but often that's limited. So that's why we're not focusing on that too much. But then there's also how far into the past do you go before it stops being useful, right?
No, I don't want to go into the past. I want to ask the question, how far do you have to collect more data before you can usefully say, suppose that an event happened at t equals 10, how far beyond t equals 10 do you need to look at stuff to actually figure out that something happened at t equals 10?
Oh, I see what you mean.
Like, for example, this would be, suppose that you're monitoring somebody, and if you're monitoring them in intensive care and they start having a heart attack at t equals 10, you probably won't catch it exactly at that point. Maybe that's too severe, but at t equals 10.5 or 11, you don't wait till t equals 20 and say, yeah, guy absolutely had a heart attack, but he's died, so it's too late, our system told us that, maybe by t equals 11 or 10.5 or 10.1, you can pretty well tell.
Yeah, sure. So I think it really depends on the data and the scenario that you have. So in our example, so the satellites I should mention too, so the frequency varies between the different satellites, but so you can get a new image every 5 days for free from some of the newer ones. And I think that will continue increasing with time. But basically, as soon as a clearing event has happened at the next closest image, so a few days later, you would be able to tell, provided that there is at least some of the cleared area visible for training. So it really is a bit of luck in our scenario in terms of where the cloud cover actually is and how widespread or not it is. But so I think that's why the uncertainty quantification in the model is really important, because like we'll never be able to say that we're completely sure. And the thing too with the landscapes is it really depends on what is being cleared and how quickly things recover. But I would say even if we were really unlucky and we had whole images covered by cloud for a couple of time steps, like you would know within a few weeks when it had occurred in that scenario. I don't know for other data, but that would be actually an interesting question. But I don't have heuristics for that as like a general rule for the model. It's a good question though.
Are you doing this in the frequency domain at all, or just or not?
No, not at the moment.
But you talked about did you talk about the spectrum in any sense or not?
Sorry?
Okay, so there's no frequency analysis in what you're doing. Okay, all right.
Sorry, do you mean because I...
No, don't worry about it. I'll ask you offline.
Okay.
If I can make sense of what I'm saying.
Yeah, no, that sounds good. I'm really interested. Yeah, thanks. Yeah, I've also heard that this would be useful for climate modeling and interpolating from like Lewis Mitchell. So I'm interested to hear what other people pick up on in things. So yeah, thanks.
Okay, so some interesting discussions there. If there are no further questions, minutes for Jacinta, we might close the session, and of course you can contact Jacinta if some questions come to mind later on. So yeah, thanks for coming along, and thanks Jacinta for the talk, and see you next time.
Yeah. Thanks for having me, and thanks for coming. Oh.